Geothermal isn't defeated by temperature, it's defeated by mechanical strength, and the fractures you can't fully control. Rock strength is a full behavior curve. Before failure, microcracks accumulate, then the system reaches a peak, and the rock enters unstable post-peak weakening. The classical engineering view is more Coulomb, a frictional shear envelope, usually combined with a tensile cutoff, for realism. At higher confinement, failure localizes into shear planes, and the failure plane orientation follows the classic geometry. Now add fluids. Water pressure reduces effective normal stress. In more space, the circle shifts, and stable rock can instantly reach the failure envelope. Griffith reframes failure as thermodynamics. A crack propagates when the released strain energy can pay for new surface energy, and tensile strength falls with larger flaws, scaling roughly with the inverse square root of crack size. In fracture mechanics, there are three canonical crack loading modes. Mode 1 is opening. Mode 2 is in-plane shear. Mode 3 is tearing shear. Mode 1 opens the crack faces. Compression closes them. Modes 2 and 3 don't open the crack. They dissipate energy through frictional sliding. Cracks don't grow randomly. As propagation continues, fractures align relative to the principal stresses, effectively searching for the mechanically preferred orientation under Mode 1 conditions. At the microscopic scale, cracks split into two families: intergranular cracks along grain boundaries, and intragranular cracks through mineral grains. Their paths become complex because local stress is never perfectly uniform. Crack growth is controlled by fracture toughness. Energy release rate is tied to the Mode 1 stress intensity factor, with the classic relation G equals K1 squared over E. Typical rock K1C values span roughly 0.1 to 3.5 megapascal root meters, from weak rocks like coal to hard rocks like granite and dunite. In the field, failure is rarely through perfect intact rock. It happens along discontinuities, depending on their orientation relative to principal stresses. That's why engineered stimulation can behave inconsistently from one site to another. Enhanced geothermal systems tries to generate fracture permeability, but stress, pore pressure shifts, friction, and toughness decide whether fractures stay useful or become unstable. Advanced geothermal systems avoids formation fluids, but must fight physics to sustain heat transfer rates. GEIOS and Nanogeios treat the subsurface as a controlled mechanical system, reducing instability, stabilizing interfaces, and improving fracture usability, while keeping the approach high integrity, measurable, and scalable. Next, decline curves, thermal drawdown, and channeling.